and I'm going to be basing this discussion on some assumptions that you may or may not have covered some of this information before, right there. So I went through pretty much everything on plotting, and have you done the tutorial for this week? I think Boz wrote together some sample programs. I know she didn't do anything with semi-log plots, that there. I don't think she was real comfortable with them either, so that there. But regardless, I'm not going to spend a lot more time on plotting. That there's a lot of things you could do more with plotting, but I mean, plotting is just one of the tools for MATLAB. And to be honest, I use it for plotting some functions, especially some of the 2D, 3D plots are really interesting. That you really haven't looked at enough functions for the 3D plots are going to be of that much use to you at this point. And as electrical engineers, I don't do a lot of 3D plotting. You know, I just don't. That's there. It's just not one of those things. If you're into, say, mechanical and you're looking at heat distribution over a surface or things like that, then surface plots make more sense. That's there. So, and there are some situations where you might look at field effects on transmission lines where 3D plotting would come in. You haven't had those courses to go through that, so I'm not going to get into much more detail there. But I'm going to jump into matrices, and I want to talk a little bit about matrices. The last class on Monday said that they have never seen a matrix before, and then I talked to Boz and said, oh yeah, it's taught in this one course, you know, that teaches the math. So I'm going to assume that you've seen matrices. That's there. So I think Monday's class fibbed to me, which is kind of typical of any class I teach anywhere. I don't care whether I'm teaching in Abu Dhabi, Fort Wayne, Indiana, you know, Kalamazoo, Michigan, or Kuala Lumpur, Malaysia. If I ask a group of students if they've covered something, they almost always say no. I don't know why that's the case. You know, they want to force me to go through it again. I'm going to go through it again anyway as review. That's it. But a matrix is basically a way of representing a complex variable of some type with a series of numbers in a, I'm going to only be looking at 2 by 2 matrices right here, right there, and hopefully I can bring up my OneNote here. Okay, and when I look at a matrix right here, if I look at, say, for example, A, and I say it's a matrix, and I'm just going to show it as a 2 by 2 matrix, and I'm just going to make up some numbers, 1, 2, 3, 4. So that is just A. Now, if I'm writing, some people will put a line underneath A to denote that it's a matrix. Obviously, when you're typing, you don't have that option up there. MATLAB stands for Matrix Laboratory. I mean, that's what it's for. It was designed to handle matrices. We've already looked at a matrix before when we define X is equal to linear space, you know, right there, and we said between negative 2 times pi, and we had some other variables up there, and then 2 times pi, right there. When we set that up, we said X is equal to, and we started off with negative 6.2328, negative 6.23, all the way down to 6.28, something that looks like that. In other words, we set up a column vector is another way of looking at it. Actually, X is, in this particular case, it's not a column vector, it's a 1 by however many row vector. You know, so we'll use the term vector to refer to a 1 by X, or 1 by N, or N by 1 vector. So this is referred to as a column vector. This is referred to as a row vector. Column vector. Right there. A column, you know, so we have that there. A normal 2 by 2 matrices has so many columns or rows and so many columns right there. So it's N by M, where right here, N is equal to the number of rows and M equals to the number of columns right there. So, you know, these are just basic two-dimensional matrices. they may or may not be square. You know, in this particular case, when we talk about a square matrix, right there, pages, let's add a new page right there. You know, a square matrix is M by M, right there. The number of rows equals the number of columns. We'll refer to it as the square matrices. For this class, I'm going to stick predominantly with column or square matrices because that's what we get when we analyze circuits. You know, so you know we're going to lean up to that there. But we could have a matrix where, say, K is a matrix, and it can look like this: 1, 5, 7, 8, 3, 2, 8, 1, right there. So this is a 2 by 4 matrix right there. It's got 2 rows right there. Row 1, row 2, and it's got 4 columns: C1, C2, C3, C4. Now, as we look at our matrix right there, we typically will give things coefficients right there, because when we write C code, if you're going to write programs in C, you would then typically have declare a matrix as a two-dimensional array. You've just taken C. Did you cover arrays in C, right? So you would declare a matrix as a two-dimensional array typically, right there. And the way we would normally refer to this here, and I'm just going to jump to a new page, is I'm just going to look at A as a matrix, and I'm just going to put it as a 3 by 2 right there, or a 2 by 3, yeah, 3 by 2. And usually we would call this A11, this one A12, A21, A22, A31, A32, where those are the coefficients right there. So if this matrix is equal to 1, 2, 4, 7, 6, 8, for example, I just set there. This here, A22 is equal to 7 in this particular case right there. So that's how we would denote the various coefficients of a matrix right there. Now, matrices have lots of things that we can look at that there, but we can declare matrices very easily in MATLAB right there. And we're going to just jump here and bring MATLAB back up here. And if I want to declare that matrix right there, and bring it back up here so that I can see it right here. And I don't know what this is right here. Right there, but we'll just leave it there. I don't know, for some reason it's okay. I guess I can get it out of the middle of that there and find my MATLAB window there right here. And if I want to declare A in this case, A is equal to, and I could declare it 2 ways. One is, my favorite way is 1, 2, semicolon, 4, 7, semicolon, 6, 8, bracket, right there. And if I just hit the enter key, it shows there's a matrix. The other way of doing it, I don't like this way because it takes up too much space, but you could actually do this 1, 2, enter, 4, 7, enter, 6, 8, bracket, right there. I prefer using the semicolons between the rows right there. That's the way that I typically would declare a matrix right there. So we could do it multiple ways. We can also, let's see, what's this? Okay, D 2 1 2. This is kind of a funky way of doing it. I've never done it this way. I'm going to skip this way of declaring the matrix. These rows may be by semicolon rather than a new line out there. That's what we just did. C is equal to D1. Oh, okay. Yeah, I see what they're doing up there. I've never done it this way, but I'm just going to go ahead and show it. You could do it this way. It's kind of a weird way of doing it. It's kind of D, and the reason I never done it this way is because I've never declared a matrix 1:5 semicolon 6:10 semicolon 11:20. That doesn't make right. (2:20). This is kind of a funky way of doing it. Let me explain to you what's going on with this method. And you see why I never use this method. I'm copying this out of that there. Is the 1:5 means that just 1 through 5. Right there. 6:10 means 6 through 10. 11:2:20 basically means that we're going to go by 2. 11, 13, 5, 17, 19. I've never declared a matrix that way because, as you're going to see, what I normally would use 2x2 matrices is to solve real problems, and I've never had a problem come to me this way. That's there. So that's why I've never used that. And you probably guess I use MATLAB for a number of things. You know, knowing all the cute little tricks that some author comes up to declare things, I don't care about. And so I don't really care about this method. I see what it does. It works great. It makes perfectly good sense. As I sit in front of a group of people and copy out of the notes, which that there, I can see what he did. But why I would ever do that, I don't know. That there. It's just one of those cases. Normally, you know, where we're going to end up with today at the end of our hour and 15 minutes, and those were at Dr. Marshall's talk, we kind of joked about that. He's programmed for 55-minute lectures. I'm programmed for 50-minute lectures. That's there. Most countries in the West, and I think even a lot of the universities, do not have 2-hour classes. 2-hour classes are the abnormal and the reason is research has shown that most students' brains turn off after 55 minutes to 75 minutes. That's there. Most professors' ability to concentrate and lecture and be productive in what they're saying shuts off after about 55 minutes to 75 minutes. That's there. I teach 75-minute classes in the U.S. twice a week, and I find that most of those turn out to be closer to 55 to 60 minutes. Because there's two patterns in the U.S. for classes. Is you can have a 3-credit-hour course that meets 3 times a week for 50 minutes each session, or twice a week for 75 minutes for each session, or once a week for 3 hours. Those classes meet once a week for 3 hours are extremely rare. They're almost always on a Saturday morning or a Sunday afternoon or on the weekend. Once in a while, they're on a Friday night. Well, and what they're geared for is people that work full time that want to take a course, you know, when they're off. That's what they're geared for. A lot of that there, and those even are broken up into 3 one-hour lectures where they have a 45-minute lecture, 15-minute break, 45-minute lecture up there, and 90% of them actually only do the first 2 hours and they're gone after the first 2 hours. That there, they never run the full 3 hours. My personal opinion, and I am new to UniKL, as most of you guessed, for the last 3 months, is really to do the 3 one-hour lectures. Those are the most productive. That there. But getting back to our discussion here, these are 2-dimensional arrays. You'll see those that there. We can look at the size of an array. I can say size D right there. Oh, and this is case sensitive right there. So that tells me that has 3 rows and 5 columns. That's all that says right there. So I can look at the size. And the reason being able to look at the size is important is because sometimes you want to write a program where you're going to be adding up the elements in that there. I'm not going to do that today, but you could write a short little MATLAB script where you're going to add up these 3 columns and create a vector that has the sum, and you need to know the size of the array for your code. I don't do a lot of programming in MATLAB. I know people that do. I use it as a super calculator up there. But again, you would want to look at that there, the size of the array if you're going to do that there. Now, one of the things you might want to look at is the transpose of an array. Now, the transpose of an array is where we just simply rewrite the array in terms of columns and up there. So going back to my array here, its transpose, this was A. A is equal to right there, and we'll just grab this and right here, just create a new page. And right there, draw. Right there, A is equal to, and should be able to just paste that. Yeah. And evidently it doesn't let me do that because I did something else first. Okay, well we'll just create a new array. We don't care. It doesn't have to be the same array. 1, 3, 4, 2, 7, 8, 11, 15. A transpose, which would be written this way if you're looking at a math textbook. MATLAB uses a apostrophe for that there. So all a transpose means is that we're going to simply flip this array around. This is a 4 by 2 array right now, and now it's going to become a 2 by 4, and it's simply going to be 1, 4, 7, 11, 3, 2, 8, 15. That's all we do is we just simply transpose rows and columns. And there's many applications as you study linear algebra where you're going to do that. A lot of this discussion here really goes back to a study of linear algebra. I don't think, again, I have not looked at your math curriculum in great detail. Linear algebra in a typical engineering program in the U.S. is a third year optional course. Generally, most people don't see a lot of linear algebra until they get to graduate school. Right there, you'll see some in terms of solving simultaneous equations and in terms of circuit analysis. You'll see some, but you don't really get into a detailed analysis of matrix algebra. Because matrix algebra, or linear algebra, is used a lot more in terms of, say, optimization theory, mapping theory, those types of things, and you don't do that as undergraduates. So you probably won't see the transpose very much, that there. So, but again, we look at the transpose. The way we do that in MATLAB is very simple. Again, MATLAB does that there. We define D right there, and I can just simply say D apostrophe right there, and that just simply transposes it. That's all it does right there. So it's very simple to transpose a matrix right there. Now, what we do a lot is we do multiply matrices right there. Now, dividing matrices is a little bit more complicated, but multiplying matrices is very easy. Now, we can multiply matrices two ways right there, and I'm going out of order, but we'll they're extracting parts of a matrix. These are okay. Matrix products right there is that we can do there's two types of multiplication that there, and I'm going to jump to that right there. One is a bit by bit multiplication right there, and let me talk about bit by bit or element by element right there. If I want to multiply, we want to go back to view, full page view. We want to. What did I have this on here before? I want to get rid of that there. Yeah, we can work with that there. It's okay. All right. So let's say that A is equal to, and let's just keep life simple. 3, 2, 4, 1, 5, 7, and B is the same size matrix. 2, 3, 5, 6, 7, 8. What's funny? What did I do there that was funny? Oh, okay, well, that's, you'll see me do a lot of that there. In this case, it doesn't matter. When I'm solving problems, it might make a difference, that there. So, okay, you'll see that. If I do what they call a element-wise product, which is a dot B, means that we're going to be multiplying each one of these elements one by one, right there. This is equal to 2 times 2 is 4, right? 2 times 4 is 8. 4 times 5 is 20. 1 times 6 is 6. 5 times 7 is what, 35? Right there. And 7 times 8 is, what was that, 42? 56, okay. I can't multiply off the top of my head. I've been using calculators too long. Right there. So I can do this in MATLAB very easily. Right there. And I need to zoom that down here. Zoom in. That there, so that I can see the whole thing there. And let me go ahead and bring MATLAB on here. And again, we could say A is equal to bracket 2 to 4 semicolon 1 5 7. Now it does make a difference if I put the wrong thing in, right? That there, because otherwise my numbers don't work. And I'm going to put a semicolon there simply so that B is equal to bracket 2 4 5 semicolon 6 7 8 close our bracket semicolon right there, and A dot B right there. Oh, and what did I right there? It should be works together. Must have the same size, and right there, and that works fine. And oh, I forgot the A dot times B right there, and that gives me what I'm supposed to get. It's not just the dot, but the dot says that we want to do it element by element. I don't do that very often with matrices, but there are times that, for example, I may want to do that there. So it's one of those things that I do on rare occasions. What we do more often is we will multiply matrices straight out right there. Now, when we multiply a matrix straight out, and so as we look at that there, turn definition of a product matrix with a vector, which is we do quite often right here, that there is that we're going to right there in home. Actually, I want to get back to my full page view. My view, hide page title. Nope, that's not the one. We want to hide that. Hide authors, full page view. That's what we had, but I want to hide this right here. Oh, there. That's what I wanted right there. So the reason is that, yeah, that there. Okay. As we look at this right here, is that is when we look at a square matrix, and this is the most common. It doesn't have to be a square matrix here, but that there. But let's just take, we've got a matrix with m rows right there. So in this case, 1, 2, 3, 4, 5, 6 rows. That's it. We got 6 rows in this matrix right here. Right here. And we're going to multiply each row times another matrix right here has to have the same number of columns right there. So if I've got 6 rows, I'm going to have 1, 2, 3, 4, 5, 6 columns right here. Now I can have as many rows over here as I want. Right there. But this has to be m. The reason is I'm going to take this row and multiply it times this column right here. Right there. So So the number, excuse me, yeah, times this column. So they have to agree right there. So we're going to end up with that there. Now what we're going to end up with is a matrix, and we're going to say that this has P rows right here. Right there, has P rows right here. And this one here has some other number of rows, but again, this is and I got this wrong here. I got this reversed here. M rows, P columns, right there. Actually, what it is the number of columns has to equal the number of rows. So I'll scratch that entire thing. I made mistake number one. So A is a matrix, and it's M by N right there. So it's got M rows. Scratch that whole last page. I just went down the wrong path there. Right here, and N columns right there. Right there. And B, in order to multiply, has to be N rows right there times, and I'm going to say P columns. These two have to match each other. Those have to match in order to multiply these matrices right there. They have to match. And let's just grab a very simple one right here. And I'm going to just copy this example. No sense making them up. I'll probably do it wrong here, but let's just simply say A is equal to 5, 7, 9, 1 minus 3, minus 7, right there. So this is a 2 by 3, right? So this is a 2 by 3. And I'm going to say B is equal to, and I'm going to just simply say, and why is this? And what is going on with this? All right. Right here, B is a 8 minus 4, 1, right there. So in order to multiply the two of these, then let's just put them side by side. A multiplied by B is equal to, and 5, 7, 9, 5, 7, 9, the last 4, 3, 1 minus 3, 1 minus 3, and the last one was minus 7, times 8 minus 4, 1. Now the size of this matrix is going to be, when we do this, it's going to be in this particular case, it's going to be this M. This is a 3 by 2. This one here is a 2 by 3, right? This is a 3 by 1. No, yeah, 3 by 1. So the size of this matrix is going to be 2 by 1 is what it's going to end up being right there. Excuse me, is that right? Yep, okay. So when we do this right here, this row times this column is going to be this value right here. So it's going to be 5 times 8 plus 7 times minus 4 plus 9 times 1. And you guys have done this before because you're correcting me as I'm doing this stuff there. That's good. So 8 plus minus 3 times minus 4 plus minus 7 times 1 right there. And whatever that comes out to be, I'm not going to do it by hand right there. But we would add that up. That looks like here. But in MATLAB, we just simply stick them in there and just say multiply. It's very straightforward right there. So multiplying matrices in MATLAB, since I'm at there, A is equal to, in this particular case, we just stick that in there, and whatever that there is, bracket 5, 7, 9, semicolon, 1 minus 3, minus 7, is that what I had there before? Right there. And then B is equal to bracket, and that was a 1 by 3. Actually, actually I did that wrong. Yeah, B is 8 minus 4. 8 minus 4, 1. Right there. But there, so A times B. And I did, and there's our answer, whatever that turns out to, what that would turn out to be. So it's a very straightforward multiplying matrices set there. And this is actually a times a column vector. I could do I could multiply two vectors that are, say, for example, I'm just going to say B is in this particular case is a 3 by 1. I can make this a 2 by, or a 2 by 3. I'm just going to make up some numbers. 3 by 2, so it's going to be 1, 2, 4, 5, 6, 7, right there. Right there. So again, when I do that, I'm going to end up with a 2 by 2, right there. So I can just simply add another row, another column to B. As long as it's got 3 rows to match the 3 columns in A, I can multiply these, and I'll just increase that there. And there's lots and lots of applications where we multiply matrices. You can't divide matrices. However, there's a special matrix called the identity matrix. An identity matrix is a squared matrix that only has 1 on the main diagonal. And the reason, and what makes the identity matrix very unique is that it's called I, is equal to, and we'll just show a 3 by 3 right there, is that if I take this 3 by 3 and I multiply it by any other matrix with either 3 rows or 3 columns, I'm going to get back the exact same matrix. There. So the identity matrix is one that exists. Well, if the identity matrix is such as that, I can take a matrix and I can find its inverse of A, which is written as A minus 1, right there, where A times A minus 1 equals the identity matrix, right there. So the equivalent is multiplying a matrix by its, right there. Now, one of the things that's very, very important is that not all matrices have an inverse. There. Not every matrix has an inverse. Now, the ones that you will look at in terms of circuit analysis will always. If you have a matrix that is generated by physical phenomena such as an electronic circuit, then there will exist an inverse for it. But if I took the matrix here, for example, I'm just going to say A is equal to 1, 3, 0, 0, 0, 0, 1, 2, 0, for example, and I try to find the matrix of inverse of that, it may not exist. I don't think this one does. A lot of times I think them off the top of my head, they do exist. But I'll just stick that one in there and see if that matrix exists there. Right there. So A is equal to, bracket, 1, 3, 0, 0, 0, 0, bracket, 1, 2, 0, right there. And I say raised to the negative 1, and it says it's singular. In other words, the term singular means that there is no matrix or no inverse exists. So if you put a matrix in and you ask for its inverse, and this is the way you ask for the inverse, is you take A raised to the minus 1, and if it comes back with this warning and you get the answer as A is equal to infinite, means that inverse does not exist. Usually, anytime you have a row or a column that's all zeros, the inverse will not exist. Right there. So in this particular case, I made up a matrix that the inverse just does not exist right there. If I said A is equal to, I'm just going to use 1, 3, semicolon, 1, 2, right there, and I say A raised to the minus 1, right there. In this particular case, I come back with, with a value right there. If I said that B is equal to that, right there. So if I say A times B, I get back to the identity matrix. So we have this special matrix that's called the identity matrix right there, and for most matrices there exists a inverse where A times its inverse is going to bring us back to the identity matrix. If we multiply any matrix times the identity matrix, we're left back with the same matrix right there. So it's a very special case when we look at the identity matrix right there. So let's make sure I'm not going to talk about sparse matrices So let me now jump into, we talked about the transpose. We can build matrices by adding two matrices together. I can say that C is equal to bracket A B. That actually is just going to put those two matrices side by side. Right there is what it's going to do. I don't use that very often. That's why I had to look it up. I almost forgot it. Now let me get down to something practical. We're going to spend the rest of the hour or whatever time we've got here talking about a practical example. And my watch is wrong. It says 8:11. It's 9:11, right? I don't know. Sometimes this watch, that's what I get for, I spent, a whole, now it says 8:11. I don't know. It's probably something I don't know. It's probably set for 2 time zones out there. So it's set for 11. All right, let's look at something that is useful as electrical engineers, and let's do some circuit analysis. So let's just do a couple of examples where we're going to look at some circuits and write these in matrix form right there. And I know that you've done these types of problems, but let's just have a circuit, and let's just do a very simple one, and then we're going to make it a little bit more complicated, and we'll finally end up with something that's very nasty right there. So, but you'll find with MATLAB it's very simple. Let's start with a very simple DC circuit. 10 volts, 30 ohms, 25 ohms, 30 ohms again, 12 volts right there. So we've got a very simple circuit, right? Now Kirchhoff's voltage law, I'm sure you've covered somewhere along the line, says that if I write the voltage drops around any closed loop, the sum is equal to 0. Right there. I always equate that. It probably doesn't mean anything to anybody in this class. I grew up in Minnesota where in the wintertime it gets to minus 30 degrees and we can get as much as 3-4 feet of snow on the ground, and that I had to walk to school and back uphill both ways, which is false because if I start at point A and I go up a hill, down a hill, up a hill, the number of rises up the hill has to equal the number of steps down a hill, right? So if I start in the lobby, I can go up and down these stairs all day long. The number of flights I go up is equal to the number of flights I go down if I end up back in the lobby. Same thing with voltage out there. If this is 0 volts right here, as I go around this loop and I add up all the drops around this loop, I'm going to end up with 0. That's Kirchhoff's voltage law. So I go into a power supply, that's a voltage increase, so that's a negative drop. So minus 10 volts right there, plus, now I didn't write my currents here, there's I1 and then there's 2 currents going through I2. Now this should be a review, you should have seen this, but I'm going to just write it anyway. Plus 30 ohms times I1 plus 25 volts times I1 minus I2 is equal to 0, right? Yeah, again, I'm just writing, this should be be that they're starting at the same point here. 25 I2 minus I1, because I'm going around this loop here, so I follow that there, plus 30 times I2. This particular time, I have a drop across the 12 volts, so it's plus 12 volts is equal to 0, right? That's Kirchhoff's voltage law. You should be able to do those, when you're asleep. Now, later on in the hour, I'm going to show you how to skip this step. We can just completely skip this step and go straight to the matrix. That there. So if I write this out, what I'm going to end up with is I've got 30 times I1 plus 25 I1. So I've got 55 times I1 minus 25 I2 equals 10 volts right there. Then we've got here, I've got minus 25 I1 plus, it looks like, again, 55 I2. Now, this is a bad example because they'd always, they normally will not come out symmetrical. When I say symmetrical, it means the top half diagonal is equal to the bottom diagonal. This particular one's going to be symmetrical. And this is equal to minus 12 volts right there. Now, if I look at this in terms of matrix multiplication right there, let me just grab this right here. Copy. And I go to the next page. Paste. I probably forgot to do that. If I take this matrix right here, go back to draw. Right. Yeah, we'll use a different color for that there. If I take 55 minus 25 minus 25, 55, and I multiply that times I1, I2, right? That's going to be equal to 55 I1 minus 25 I2. Remember, this row times this column right there, minus 25 I1 plus 55 I2. And of course, we know that to be equal to 10 minus 12 right there. So we could write this in a vector form saying that 55 minus 25 minus 25, 55, I1, I2 is equal to 10 minus 12 right there. So we rewrote this problem as a matrix problem right there. So what we can simply say is that in terms of a circuit, we're just rewriting this. We're going to call this R, call this I, and call this V, right? Ohm's law says that R times I is equal to V. Now, normally you say IR is equal to V, but we're going to reverse the order there. It's right there. Well, if we know R, we can find the inverse of R, because our unknown in this case is I. So if I take R minus 1 times R times V equals R to the minus 1 times V right there, these two break down to be the identity matrix, so they disappear right there. So our unknown I is equal to R to the minus 1 times V. So we can now solve for our unknown currents very easily right there. And you're shaking your head. Have you? Now, she hasn't done this in the lab, has she? Out there, probably not. But you've seen these systems of equations before. Have you ever looked at them from a matrix standpoint? Have you seen this approach before? You have seen that there. So now what we're going to do, we're just going to stick this in the MATLAB right there. is all we're going to do. Again, I'm going a little bit in the dark. I don't know what was covered in your circuits course. Was this covered in your circuits course? Is where you've done that there. So we're going to do this out there. So we now have our out there. So again, all I'm going to do is just stick this into MATLAB right here. And I'm just going to say that R, and let's get back to the right window, R is equal to 55 minus 25 minus 25, and I don't know why that's purple, but we'll find out here. 55, and so I got this, and so, oh, I left the equal sign off. Right there. Okay. And that's typical. Usually Monday mornings I forget this, but this is still morning, right? I haven't had my second or third cup of coffee yet. Right there. So all right. So R is equal to that. B in this particular case is equal to 10 comma minus 12 right there. Right there. So I is going to be equal to R raised to the negative 1 times V right there. So those are my two currents. How do we, now what I like to do typically is I like to verify that, and the easiest way to verify that is to, and this is what I discovered Monday. I did not have this software installed too, so that's why up there, wherever it's at, you can see all the software I've got installed. No wonder my computer's run so slow. I'm looking for OrCAD. I passed that there. Silicon Labs. Okay. Schematics. This is the software. So I'm just going to stick this circuit into MATLAB. I don't know what. I think you probably use Electronic Workbench for your circuit analysis program. That there. What? Which one? Multisim. Okay. Multisim's. Their simulation package is called Electronic Workbench. It used to be called that. I'm an old time. Electronic Workbench, Multisim is now that there. PSpice is the one that's been around for decades and decades. It was actually a university project back in the 1980s. That's there. And the early versions, you actually wrote the net list out yourself. You didn't draw the schematic. That there. The more modern versions. That there. And so I still use OrCAD. OrCAD bought PSpice out, and now it's part of a package that now is done for laying out circuit boards. It also does simulation. So I tend to use that one. It's the old school one. It's a little bit more. I don't know what to say. Once you get used to it, it's hard. It's hard to change. And it does a lot more than Multisim, to be honest with you. It's a more powerful package. But it's not as easy to use. But let's go ahead and we're going to place a part here. Oh, and I probably need to place part. And what is going on here? It's not finding my get new part. Oh, okay. So, and I didn't draw my circuit here. I had what, 3 resistors? Is that right? Two. I didn't have one in the middle there. All else fails, put the circuit up there. Okay, 30, 30, and 25. All right. Right there. So, and then we had two voltage, so that's a VDC, 2 voltage sources right here. And then we always have to put a ground, a ground right there. There's our ground point, and then we just simply wire things up here. Yeah, it's very similar to Multisim. It's just that the other thing is this software is free. and I like free. Multi-sim, the university has to buy a license for it, and that doesn't cover personal computers, so I use free. That there. This was what, 10? Well, it's 12, but when I draw the loop, it becomes negative 12. And this was what, 30 and 30, and this was 25. Right there. So we need to save this, and I'm just call it. I hate to save it in documents. That's junk. The reason I call it junk is that I know later after class to go through and delete everything called junk. Right there. That there. Because I don't want to save this forever. These files just take up space. So there's our circuit there. We can do our analysis right here. Right there. And really basically the only thing you're going to do right here is we just tell it to simulate. It doesn't do anything here other than it's going to bring up a program called probe, which we're not interested in using right here because right there. That there because we don't have any output waveforms, so we just close that there. That there. Yeah. All right. But what are you wanting to do? Right there. Yeah. Well, the analysis right there is that we want to tell it to show the current there, and maybe I need to run it again. I close. Yeah, okay. So there. So here it's showing my various currents right there. Now, the key thing here is if we were to look at and let me bring this here, and we don't want to do that. Right here, and we look at my there. Is that large enough? You can see that on the left there. You can see those currents right there, 104.17 milliamps. See, and we come back over to here, and we can see that they do agree. That there. So now the thing here is, this one here is a negative number, but if we come here and we click on that, you can see that arrow is going in this direction. So we can see that we drew I1 going clockwise. In reality, it's coming out of the positive side of the 12 volts, and it's going counterclockwise. So that's where that negative comes from. That there, both this one is going down and this one is going down. So as we look at this current here, right there, this is 275 milliamps. That is the sum of these two. If I was to add 0.1042 plus 0.1708, I got that's right, 275 milliamps up there. So our simulation matches exactly what we would get right there. If we were to build this circuit in the lab, we would expect to get numbers plus or minus 20%, because resistors we know are plus or minus 20%, right? So we would get numbers similar to that there. So it's a very easy tool. Now, this doesn't save us a lot of time because it's a 2x2, right? So you can do that on your calculator if you've got a modern calculator. Most modern calculators, I don't know which calculators everyone buys, but they have a matrix input mode. But let's go through here and let's kind of go through a much nastier looking circuit there. I'm not going to do the PSpice for this, because the reason I'm not going to do the PSpice is that it would take me more time, because I'm going to cheat and just put down impedances right there. So actually, let's just stay with the DC out there. And let's do a circuit that would take you a long time to do out there. Because when you solve this circuit right here, when you solve this matrix here, you most likely you did not do the inverse method in your circuits class, right? You did? No. You used determinants, right? All right. Determinants don't work very well when you get beyond a 3 by 3. I suspect that the largest circuit you dealt with in your circuits class was a 3 by 3. And a 3 by 3 was a nasty thing, wasn't it? You know, a 2 by 2 is easy. It's 25 times 75 minus 25 times negative 25 times negative 25 is the determinant underneath. The top is, you know, I1 is, you know, 10 times 55 minus 12 times 25, right? At there. In other words, the way you solved this was your determinant was 55, and the way that you would normally write this is you would put a bracket there, minus 25, minus 25, 55, and that's equal to 55 squared minus 25 squared in this case, right? And so I1 is equal to the determinant of 10 minus 12, 20 minus 25, 55 over delta, right? That's the way you solve that, right? That there. And when you got to a 3 by 3, then you had to do 3 of these, right? You know, the determinant of a 3 by 3 is XXX, XXX, XXX. You had to take this times this times this, right? And then you subtract it from this times this times, you know, that there. Nasty, right? All right, we don't do any of that here. If we want to find the determinant, by the way, let me just point this out here. That there, I believe it's just DET. I don't usually use the determinant, but if we want the determinant, we can just simply say DET R right there, and that tells me what my determinant is right there. So we can find the determinant very easily right there. So, you know, the DET, it does find the determinant. But let's look at a 4 by 4, which again, I know that you would not do a 4 by 4, and we're going to finish our hour with a 4 by 4, or hour and 15 minutes or whatever right there. So I'm just going to make this circuit up here. It doesn't matter. You know, I'm not going to say these resistor values down as I write them, because I'll probably say something different and give you guys something to laugh about. Right there. 20, 30, and I need to, in order to do this, well, let's just go ahead and stick one up here. Right there. And then we'll right there, 40, 60, right there, 20, 40. All right, there's a, I guess we need to finish these right here. So there's a nasty looking circuit right there, right? You probably didn't see anything quite like that in your basic circuits course, right? This is child's play. This is really child's play. It really is. Again, I'm going to define my loops, and I'm one of these, a lot of people think of engineers in terms of the way they think. I like to think in terms of a logical process. So I draw all my loops clockwise on the inside, starting left top and down right there. So if I do that, I'm going to draw all my loops right here. This is I1, I2, I3, I4 right there. Now you can draw your loops however you want. I just do it one way. That way it just keeps life simple. And I should point out that if you do it this way, 90% of the time, all your everything off the main diagonal is going to be negative. Now, I'm also going to show a shortcut method here as we do our matrix here, and I'm going to explain this. You can go back, watch the video that there later to pick up the highlights of this. But when I look at this matrix here, and before I do this, let me lasso this so that I can copy this to the next page. Right there. I forgot to copy it, that's why it didn't work the first time. That there. Okay. That there. So that when I actually do the matrix, but when I look at the matrix right here, right here, is when we look at the matrix right here, what we know here is this row is everything in loop 1, loop 2, loop 3, loop 4. Because when we write our equations, I go through and write the equation here times this column, right? So if I'm going to write the equation, this first equation is what I would get when I go around loop 1. This is everything in loop 1 that I'm going to multiply times I1. This is everything in loop 1 I'm going to multiply times I2, I3, I4, right there. So instead of writing the equations, I'm just going to look at the loop and fill in the data. So let's just start this and I'll go to the next page. In loop 1, everything in I1 around this loop, I'm going to multiply times I1. So it's going to be 10 plus 25 plus 15. So I'm going to write 50 there, right? So I'm going to put a 50 right there. Now I2 is right here. And the only resistance that's shared between I1 and I2 is the 25. See? So when I look at loop 1 and loop 2, I've got one resistor that's in common between the two of those. Is this 25 ohm resistor right here. So when we look at that there, and then we look at the arrows, which direction? Are they going in the same direction or the opposite direction? So if it's in the opposite direction, I put a minus 25 there. If they're in the same direction, I put plus 25. Now, between loop 1 and loop 3, do we have any resistors in common? So I'm just going to write a 0 here. In between loop 1 and loop 4, do I have any common resistors? I just write a 0. Now, this is where the shortcut comes in the fact that if I was to write for loop 1 or loop 4 and I'm doing for I1, if I don't have anything in common with I1 and I4, when I do the first row, I'm not going to have anything in common when I do the fourth row. So I can just go ahead and put that 0 there. I can go ahead and put this 0 here and this minus 25 here. So I can fill in, I can fill in that row and this column the same. This particular matrix is always going to be symmetrical. The top and the bottom is going to be the same because of where it's coming from. Right there. All right, loop 2, I've got 3 resistors, a 25, a 20, and a 15. So that's looks like 60, right? So I go ahead and write the 60 right there. That comes from 20 plus 25, that's 45, plus 15, that's 60. Between loop 2 and loop 3, I've got one resistor, 15, right? This is the one that's in common between. My 15 doesn't look very good, but this is 15 right there. So, okay, my 15, I2 is going down, I3 is going up, right? So it's going to be minus 15, right there. Now remember, as I do a row, I can do a column, so I go ahead and put that right here. So I write that twice. Between loop 2 and loop 4, there's nothing in common, right? Here's loop 2 going around here. Here's loop 4 going around here. We have no resistors in common, so we put a 0 here. Right there. So as we go around loop 3, I've got 40, 60, 70, 100. 40 plus 20, that's 60, plus 30, that's or 90 plus 40, that's 120, right? My math was wrong the first time. Is everyone get 120? That there? 40 plus 30 is 70, plus 90 plus 40, now I get 130. Is 130 the right answer? Let's go through here. Now I'm having the brain. What did I say? After an hour, the brain shuts off. You know, we're at an hour and 10 minutes. You know that there. So we're at 60, 90 plus 40, 130. So 130 is the right answer here. 130. Between loop 4 and loop 3, I've got just the 40, and they're going in opposite directions. And then in loop 4, I've got 3 resistors. It looks like I got 150 there. 50 plus 40 is 90 plus 60, 150. So there's my R matrix right there. You know, just by looking at the circuit, I came up with my R matrix right there. So there. Now our V matrix, or vector, we just add all the voltage rises. Now it's opposite of the Kirchhoff's voltage law because I'm looking at increases. So we're looking at the easiest way I do it is the sign that the arrow's coming out of is what I use. So as I go around loop 1, right there, I've got one power supply, and that's a 40 volt supply, right? So, and I'm coming out the negative side, right? So I would write negative 40 right there. Oh, excuse me. Loop 1, I've got 0. Loop 2, I've got minus 40. Loop 3, I'm coming out the positive and coming out the negative, so I end up with a net result of 0. And then loop 4, I've got nothing. So that's kind of interesting, is that we only end up with one value in there, negative 40. We'll find out whether we're right, because I'm going to stick this in the MATLAB, and then I'm going to stick it in the PSpice, and we're going to see if they agree. Yes? Which one here? 3? Oh, this one should be 90 here. This one here. 105? Okay. All right, let me just double check that. Just simply because, so I've got 15. Okay, I use 40. That's where I screwed up. Okay. I see. Yeah, you know, and remember, it goes back to my original research. I said after the hour, the mistakes start popping up. That there. So yeah, which is bad for you because you have a 2-hour final exam, so you have to figure out some way for your final exams to keep the brain working for 2 straight hours. That there. So that there. It goes against all. 1-hour exams, I find students do very well. That for some reason, when you get to the 2-hour final, keeping the brain going, which also tells me that if you've got a problem that you have a question on, that there, don't leave it for last. Do the hardest problems first while the brain is still fresh. So, all right, we're going to go ahead and I don't know how I'm going to do this, but let's. Trying to get this to where, okay, I can see all that on the screen right there. All right. Let's go ahead and bring MATLAB up there. And again, I'm just showing them side by side. That way I can see that there. So in this particular case, R is equal to bracket 50 minus 25, 0, 0, semicolon, minus 25, 60, minus 15, 0, semicolon, 0, minus 15, 105, minus 40, semicolon, 0, 0, minus 40, 150. And thank you so much for correcting my mistake, because I have had classes where students do not correct my mistake. I get all the end, and I get the wrong answer, and all right, why? And there's, well, you made a mistake back here. Do it. Correct me when I make the mistake. That there. So now let's just go ahead and put B in. B is easy. Oh, we got to go over here. B is equal to 0 semicolon minus 40 0 0 right there. So that's right there. So I is equal to R raised to the negative 1 times B. And those are my currents. Now I'm going to go ahead and I'm going to put the circuit in PSpice right there. We're not going to check all the currents, but we can check the ones that are by themselves and see whether or not they match right there. So that there. So there's our currents. So if I go back to my circuit here, right here, and this is why I put the circuit there, I can see that I1 I should have between these two resistors, the 10 ohm and the 15 ohm, I should have 443 milliamps. Through the 20 ohm, I should have, that's I3, I should have 141 milliamps going in this direction, from right to left. In the 20, I should have going down, or going up, 141 milliamps. Through the 50 and the 60, I should have 37.6 going from right to left. So as I draw my circuit right here, I should be able to check enough of the currents to see whether or not I've got the right answer. So let's go ahead and bring up right here, and this is rare that I've got to the point where so I'm going to just go ahead and delete this circuit here. Right there, delete the whole circuit. And where's my delete key? All right. Now we know. There's my. It hasn't moved. It's been the same place on this keyboard for 4 years. So let's go ahead and do a draw. Let's go ahead and place part. And we're going to place a resistor. And let's just go ahead and do all the ones that are going up and down first. There's one here, there's one here, there's one here roughly, and then there's one up here. Let's rotate this. There's one here, one here, one here, two down here, and one here, right? That should be all the resistors roughly, right? All right, let's do a power supply, Control G, BDC. We should have two power supplies, right? Right there should be one right here. And this should be rotated, and this should be right here. I'm going to have to probably move some of these parts around in order to give myself room. Right there. Okay, does that look like they're pretty much? We'll know when we start drawing, right? Right there. So let's just go ahead and draw this one up. Draw this one to here. Draw this one to here. And again, the software that you're used to using, actually let me move these over to where it's right there. Guess I can move these up closer right there. and this particular, does that look close to the circuit? I think I got everything covered there. So let's just go ahead and put the resistor values in there. That's a 20. Now this is where you really have to watch me, because this is where I'm going to 10. Out there. I'm ending the hour here at 25. Right there. This is 40. This is 15. Actually, those are reversed, aren't they? Everyone see that I've reversed these two. That doesn't make a difference. They're in series. We can leave them out there. This is 30. This is also 40. 50. 60. And I forgot this one here. That's the 40. Okay. Did I miss one here? Oh, this one here. Okay. Now we've got everything. Does that circuit look the same? So let's go ahead and save it. Let's do a simulate. Again, right there. And let's then, and I'm going to bring up the MATLAB solution, because that's what we're comparing this against right here. Right here. And see, so as we look at that one there, I1 is 443 milliamps. It's negative, which means it's going in this direction. What do we have for MATLAB? This here is right there, 886 milliamps. Again, it's going down instead of up like I'm supposed to. This is my 36.6 milliamps right here. That matches this pretty close. Yeah, exactly that there, going the right direction. So as you can see, the MATLAB that there, and I would challenge you to go back to your circuits class and find a 4x4 problem like this and solve it in this amount of time. That there. So you can see where MATLAB, and the same thing would go if we had a 5x5 or a 6x6. It's just, this is where MATLAB really shines in circuit analysis. That there. So with that said, we've got one last thing, and that we actually use up most of our time today, is I have to do the attendance thing. And actually, I don't know if I can do the attendance thing, to be honest, because I think last week I tried to do it and I don't have access to this class. Is that right? So I'm probably wasting my time doing this, but we'll see. That there. And actually, it looks like I'm wasting my time because I can't even get to the portal. So, all right, I'm not going to worry about attendance. All right, that's it for the day then. We actually used up almost all of our time, didn't we? This is unusual. Well, an hour and 18 minutes. That's